So we're a little bit ahead of our larger schedule. So I do want to ask, Gary Stephenson was up next. Gary?
I'd be happy to go a little early if you'd like.
Yes, if you'd like to. I should do my
Sure.
Gary Stephenson intro though. I don't have one. I don't have it queued up though. Well, do you want to just start? You're regular here, so I've done your intro in the past, sir.
Sure. Yeah, I've given a couple of talks here before for Tim's group. We go way back to my Seattle days, and I've always had an interest in advanced propulsion. Most of my time's been spent, in terms of advanced propulsion, studying gravitational effects and field manipulation and things that are way out there. So the paper I want to give today is a much closer in technology, and one I'm frankly a little befuddled doesn't get more attention, and that's Magnetohydrodynamics. And so that what's motivating me to give today's paper is, yeah, it's great to look at gravitomagnetics and gravitational manipulation, all this fire out stuff. It probably aligns better with what we're seeing with UAPs. But just to get started with the more electrification of aircraft, I think that the magnetohydrodynamics is a much closer in, much more near-term technology, number one. Number two, my day job now is with electrified aircraft. It's with Whisk Aero in Silicon Valley, and we're developing electric eVTOLs. These electric VTOLs are battery-driven. They're fully electric. They use no hydrocarbons whatsoever, but they're very limited. They're very limited in speed. They're very limited in range. And if we could switch out from these pretty old school Tesla motors driving these basically fans, air fans, these lift fans that lift our vehicle up, and then these air fans that push our vehicle forward, we would be a lot better off with more advanced technology. So that's what piqued my interest in this Mhd technology. The briefing I'm about to give was first going to be a business plan in 2008. It failed as that. It never got fully developed. And so the bones you'll see to this briefing are along the lines of that business plan. So with that, I would like to share my screen and go jump into the paper. Does that sound all right, Tim?
Yeah, absolutely. Absolutely.
And let's see, the view here is covering up. The icon that I need to click on. Let me shrink this down. There we go.
Okay, perfect. And it looks like it's showing an executive summary also. I'm not.
Yeah, let's see here. Let's see if I can go to just a plain old full screen. Yeah. Well, it might be better if I just displayed it this way, because we don't need to see the next slide.
Sure. If I could ask, do you think that you could maximize the?
Sure. How's that?
Yeah, that looks good. Yeah, I think that'll work great. Okay. Well,
Okay.
let me mute myself out. And again, thank you for presenting it. And yeah, this should work great.
Sure. Yeah. So it's titled The Future of Mhd in Aerospace. Of course, I can't predict the future. So this may or may not be the future. It's one potential future. And in this future, in this parallel universe, we are taking advantage of this quite incredible technology for the electrification of aircraft. It was originally based on a business plan. It's going to be presented in 4 steps. There are control surfaces that we may be able to add to aircraft to assist with drag and assist with maneuverability of aircraft that are Mhd related. If we wanted to do a half step on the adoption of Mhd technology, we could convert just the engines, the lift engines and the forward thrust engines to Mhd. We can also look at a more efficient design that incorporates MHD into the actual skin of vehicles called blended wing body. And then finally, if there's time, I wanted to go over an idea that's been kicked around on using Mhd bypass for a single stage to orbit vehicle for basically first stage to LEO for space travel. Outline is based on these original business objectives. I'll probably, because it's more of a technical group, downplay the business objectives and the program schedules. These schedules are somewhat aspirational. According to one of my reviewers, at least, they would be a little bit challenging to hit. But I think it's better to have goals than not. And so we could treat these as target goals for now. I first wanted to back up and go over a little bit of background on what is Magnetohydrodynamics and how do they work. They work using the ionization of air. So it's got to be an ionization of a fluid. For marine vehicles, it's ionization of water. For air vehicles, it's ionization of air. Once you've ionized the air, then you can use electromagnetic forces to control the airflow. If you don't ionize the air, you can't do that. So all of this MHD technology, including Faraday and Lorentz forces, are being applied to charged air. The charges are what moves the air. So some examples here, I have a diagram, not a very good diagram from Wikipedia, showing that there can be magnetic generators, MHD generators and MHD accelerators. In an MHD generator, you have charged air flowing through a cavity, and that cavity has a winding around it. And that winding then will wind up generating, because of the field generated, because of the flow of charges, will wind up generating a current. So you're using that ionized airflow to generate a current, essentially power generation. You can also take power and apply it to the flow of ions through the same cavity, and that's the accelerator. So you're using power to accelerate your charged ions and your charged airflow instead of the other way around, taking that charged airflow and generating power. So you can use it as a generator or as an accelerator being an engine or a thruster. The strongest of the two forces is the Lorentz force if we're using fairly large electric and magnetic fields. And the Lorentz force, F, is equal to the current density J cross product with the magnetic field B. So, and the cross product is really the key thing, and it makes it, Lorentz force is very difficult and very non-intuitive in terms of understanding, because a cross product means you're orthogonal to both the other two vectors. So if the J vector is the ion current density flowing through a cavity, let's say on the picture on the right, that we're flying an aircraft with an MHD engine, and there's airflow coming into the engine, and we're using a very large electric field to ionize that airflow as it enters the engine. Then that ion flow through the engine is J, so you can see that vector J. And then perpendicular to that, into the body of the aircraft, we have an extremely strong magnetic field on the order of a couple Tesla. Then the resulting force isn't along J, like it would be with a regular thrusting motor. It's orthogonal to both J and B, and would be a lifting force that lifts straight up. Put another way, the engine's providing the lift, and there's no need of wings, which means you have a lot more flexibility in terms of airframe development, right? You can develop airframes without any need for wings, which should be really handy for flying cars. We already went over the accelerators and decelerators. The accelerator would use applied power to accelerate the ions and create thrust. A decelerator is really a generator, and it's taking the energy from the ion flow and is creating electric power from it. You can slow down air with the decelerator. You can speed up air with an accelerator. You can micro-miniaturize these into the skin of the aircraft and use these accelerators and decelerators to number one, reduce drag and turbulence. Number two, act as though they are control surfaces. You can also reduce friction, and you can mitigate sonic booms because the airflow isn't as disturbed around the vehicle. So we touched on this a little bit. I want to introduce the concept of a wall converter, Mhd wall converter, also referred to as a parietal accelerator or linear accelerator. Let me back up here. In this configuration, this is a channel engine. This is Mhd channel. It's just an empty channel. And so that's one configuration of an Mhd engine. Another configuration of Mhd accelerator would be a wall accelerator or a parietal accelerator. And in this configuration, you don't have, there still have to be orthogonal for Lorentz force. But what you're doing in this particular case is you're alternating the direction of the B field and of the ion flow in a way that is alternating back and forth. But you're paying attention to your signs so that the Lorentz forces always line up in the same direction, which typically you would want it to be in the direction of the flow of air. So this ion flow is very small scale flow that's going perpendicular to your main flow of air and your main Lorentz forces, as is the B field being perpendicular to both and typically radiating out. If this is a cylindrical object, the B field would be radiating out. The ion flow would be around the outer perimeter of a cylinder. And then the Lorentz force would be along the flow of the cylinder. And we'll show that cylinder shape, call it a tic-tac shape if you'd like, in a little bit. But this is a typical wall converter that can also be used for replacing ailerons, rudders, flaps. These control surfaces that are typically mechanically actuated could also be done with the skin of the aircraft. This was all studied in the early 2000s by Air Force Research Lab. They had a multi-year study. It went on for almost 10 years. This was the cover to their interim report, which is very interesting reading. I didn't see the final report, which leads me to believe that the final report may not be publicly released. The interim report was publicly released and is available, and you can look up that document number and just Google it and find this report. So I won't dwell on too much of the detail, just the high levels. You'll see the name Shang and I guess it's called Sarakov. Shang and Sarakov were the principals in these investigations, and you'll see their name on many of the papers that came out of this study. The study resulted in almost 100 academic papers over the 10 years that was running. One of the better ones, in my opinion, and Shang and Sakharov published together, was mechanisms for plasma actuators. So when I talk about actuators, we're actuating a plasma flow. You have to use ions, right? And it's an ion, it's a weak ion plasma. And they're using them for actuators in situations where you literally cannot have mechanical actuators, for instance, hypersonics. In hypersonic vehicles, the actuators wouldn't hold up, right? I mean, you can't operate mechanical actuators that survive at Mach 5.5. But in these papers, they did exactly that, and they were testing them at Wright Pat near Dayton, Ohio. And you'll see we were combining forces here with the Russians. Russian Academy of Science is where Sarakov is from, and Shang is our guy at Wright State Air Force Research Lab at Wright Pat. They did a lot of really good modeling. It's very difficult. Plasma modeling is a black art more than a science. And they started with the Boltzmann equation for weakly ionized gases. They go through all of the approaches here on how they did optimize these simulations for ion flow. But the bottom line was they were pretty close when they compared the data with the computationally computed simulation. The simulation are the lines in the middle in terms of these ion densities. This is ion density plotted as a function of distance along this particular actuator. And they're showing the number of densities, like 10 to the 10th. This is per cubic centimeter. So this would be considered weakly ionized because we're at like less than 10% of the atoms or molecules within the airflow are actually ionized. So you don't need to ionize every single molecule to have an ionized flow. If you can get 1%, 5%, you're going to be able to manipulate that flow. This shows a typical example of not having a Lorentz force versus having a Lorentz force. The top is a ramp, an air ramp that they set up at, I think it was Mach 5+, according to the text there. And you get this stagnation area where there's turbulence. And then if you run it with a B field, then suddenly that turbulence goes away. So this is just a typical example. They're pointing out you can get a 7-degree ramp with spending only 350 watts to generate this plasma. So this is a very important experimental result. It tells you you don't need to expend a lot of energy to make these Mhd actuators work. The business case, I'm not going to dwell on it in the interest of times. Obviously, there would be some fuel savings according to drag reduction. There's going to be additional weight and power needs by embedding these wall accelerators or actuators in the skin of the aircraft. There is weight and power associated with that. But as you may recall, there's also weight and power associated with these linear actuators that actuate the flaps and the rudders and the ailerons and slats of a typical aircraft. So those don't come for free either. This is just a typical program schedule that you would see on any development program of a new component or aerospace component, where you would really want to do a survey first, decide whether your industrial research and development funding is justified, find some academic partners, do some internal research and development, and then maybe develop a lab, develop some devices, and then certify those devices for use in an aircraft. This caught my eye when I was looking at this paper of Petit. If you look at figure 20A down there, doesn't that look like an awful lot like a Tic Tac? I'm not saying it is because Tic Tacs move at like 800 G sometimes. So, but it was striking to me how similar it looks. This was a drawing by Petit. He's a French aerodynamicist. He's published extensively on this since the 1970s. So unlike in the US where we're kind of on again, off again, I think the French have had a very long and consistent development program and research program in this area. And they're not afraid of the topic and they publish routinely on the topic. So when we get really interested in something, we'll really hit it hard with a hammer, as in the AFRL study. And then we kind of forget about it for a while. And so it's been very on and off again here with MHD in the States. MHD engines work by creating these Lorentz forces. It's important to remember the Lorentz forces that created by these engines are far in excess of the inertial forward forces that will be represented from the fluid mass displacement along the skin of these motors. So if we have these tic-tac shaped motors that are attached to wings of an aircraft, say for instance, and we're developing a linear force, that linear force is not from the flow of that air. That linear force is from the Lorentz force developed by ions encircling in cross-section, encircling that tube and the B field that's being radially radiated out of that tube. That's what's creating that linear force of the Lorentz force along the flow of the air. And because it aligns with the flow of the air, it does control the shape of the flow, which reduces drag. So if we were to retrofit conventional aircraft with MHD devices, that it very likely would be the shape of an MHD device that provides thrust, forward thrust, because that is the shape you would need for a linear backward-facing force that you would normally see from a regular either propeller or jet engine. Conversely, you also could have discs that are like lift fans. My vehicles at work have lift fans during the takeoff and during landing that either lift them up off the ground or slowly buffer their landing so they don't come down too fast. And these lift fans are propeller driven right now, but if we wanted to retrofit, we could get these biconvex shapes They're called Biconvex Aerodyne because it sounds more scientific, I guess, than flying saucer. These biconvex aerodynes are very, very counterintuitive as well, because the airflow is coming off the top and then sliding along the bottom. And that airflow is manipulated by the Lorentz forces being developed within that shape. So I don't want to delve into detail, but I will show the diagram E, if you can see on the bottom, shows what would typically happen without Lorentz forces. And then with Lorentz forces, this thing is really pulling a lot of air along around the edges of it. And the Lorentz forces are being pointed straight down. And so that those two things, the drag reduction along with the resultant Lorentz forces, mean it's a very effective and efficient lifter. Obviously, these are electrically powered. So if you had hydrogen fuel cells or some other clean electrical source, you're not burning hydrocarbons. So that makes a very strong green business case. There's very little technical research done on this because in the past, the Air Force has been interested in MHD for very high-speed vehicles. This is the way you electrify fighter jets or single-stage to orbit or hypersonics. So their interest has been more in the hypersonics, not in subsonic. Subsonic's not that hard, we know how to do it. And so we haven't really looked at how well these devices operate in subsonic. So there would be a big challenge here in terms of developing these. So I think I show that here, that there's a much longer timeline in terms of developing a lab, the risk reduction needed for engine development, and so on. This lower diagram here isn't the wall converter, it's your traditional MHD channel engine. And there was a paper by Lee and Sykes, I think it's Paul Sykes, who I've seen at advanced propulsion conferences over the years, trying to calculate what is the weight of this thing. But I think this paper was from the 1980s, and this was before, people like William Ryken started developing superconducting nanowires that dramatically shrank the size and weight of the magnetic windings you would need to create a couple Tesla. And so we would really want to revisit these mass estimates in light of this very advanced wire superconducting technology. Finally, I wanted to get to the blended wing body concept, where the body itself is part of the aerodyne. This is the Mhd aerodyne shape that Petit, French aerodynamicist, first proposed. And it's very much like the lifter design I was talking about a couple slides ago, except that it's the entire vehicle. So everything and everyone that you want to put in the vehicle is on the inside. And this diconvex or biconvex aerodyne is essentially the skin of the aircraft, is what's creating the Lorentz force and providing propulsion. I will get to a different version of this when I give my acknowledgements, because there was another version of this I wasn't aware of. This is the French version. There's another inventor that had a very similar version, but that used a laser to help pre-ionize the air so that you wouldn't want to necessarily depend upon just skin ionization. Obviously, this is going to be a very long development timeline too. We don't even have blended wing bodies right now with traditional engines. So this would be quite a stretch and a very different paradigm in terms of developing air vehicles if we wanted to go this route. It's also not going to be airworthy. You can't glide down onto the Hudson if it loses power, right? Because there's no wings. So there's no glider capability with this thing. So you would need safety parachutes, as our current vehicle does. Our eVTOL vehicle has a safety parachute should we lose power. Aspirational again, but assuming we already had the control surfaces, that technology, and Mhd engine technology behind us, then leading up to this, that being a given, we could then continue one step further and go on with the blended wing body development. This is what the whole thing looks like, putting it all together. Proposing like 4 years of IRAD in this area. The control surface development should come first, but can overlap with engine development. And then the engine development can overlap with the blended wing body aerodyne development. So this is one potential future. for MHD adoption. And it is a little bit aggressive, I'll admit. But yeah, it's better to start somewhere and start down this path and see what kind of progress we can make with these devices. Before I get off the stage, I wanted to bring out, because this gets a lot more press than the traditional MHD for regular aircraft, as this notion of a single stage to orbit Mhd bypass concept. So what's an Mhd bypass? Mhd bypass uses a generator to slow down hypersonic flow, and then an accelerator to add the energy back in. So say, for instance, this is a vehicle that was proposed in by Cezanne, a Frenchman in the early 2000s, after some discussions with the Russians on a vehicle that I believe we have dubbed Ajax. And this would be either a almost to orbit skimmer, atmospheric skimmer, or a single stage to orbit type vehicle. And our guess as to the internal workings is that the MHD generator would slow down and tap the energy off of the incoming hypersonic flow and would bypass, that energy would bypass a SCRAM engine, supercruise or ram air engine. And then it would add that energy back in on an MHD accelerator at the end. So that way, even though your SCRAM engine might be limited to Mach 5.5, you could go to higher Machs outside, tap that energy off on the MHD generator, which would slow it down to Mach 5.5, where that SCRAM jet is still functioning, and then add it back in on the back. That's the concept, and I don't know to what extent the Air Force has tested this concept. And I don't really have a clear vision for why we would do this in two stages. This particular vehicle had two sets of inlets. We don't quite know why. One might be a two-stage motor, one that's operating slower, one that's operating more at a higher Mach, or this could be just a rocket engine that doesn't need a generator or accelerator at all. It's just a straight rocket engine. And when you get to a certain point and you run out of atmosphere, and say you're at 10 or 15, Mach 10 or 15, you need to get to Mach 30 to get to orbit. It just takes over as a traditional rocket and flies you the rest of the way to orbit. So that is an interesting concept, and Seiss and Lee have published on that in the 80s and 90s. Obviously, this would dramatically reduce the cost to orbit because this is a fully reusable vehicle. So very much more inexpensive way to go to LEO. It probably, because you run out of air, and that's one of your propellants is this external ionized air, you're not going to be able to get very far beyond LEO given just this vehicle. But at least you get to LEO, and that's half the battle. Technical challenges is has been tested at very high Mach. And even just regular scramjets at Mach 5, you know, is right now pushing state of the art. And we've had limited success with this. We've heard the Russians and the Chinese are doing a little bit better, but it's a area of active research just getting scramjets to work, let alone with bypass mode. Post-development, obviously, sky's the limit on these LEO launches, and you can get to GEO with an inertial upper stage. Here's a bit of a timeline. I'm presuming this would start after we've already done blended wing body, but not necessarily. There's no reason why we would want to wait that long. Once we've gotten the technology down for control surfaces or MHD engines, this is just one more glorified MHD engine, albeit at a much higher Mach number. This is called the Wave Rider configuration. It's another vision by Petit, how you could combine some of these wall converters, and you could use that as your generator and accelerators built right into the skin of the vehicle, where you don't have to do it on the air inlet, you're doing it on the skin itself. And with the Wave Rider concept, you can kind of skip around the globe where you're sucking up a little atmosphere and jumping out, sucking a little atmosphere and jumping out, and you're kind of porpoising around. So this would be a very high-speed way to get around the globe without truly getting all the way to LEO. All right, my wife points out greenhouse gases are zero with these electric propulsion schemes. Conclusions, I don't really have any other than it would be fun to try this. It would be, I think, good for the environment to try this, to fully electrify, not just these putt-putt vehicles like what I'm working on, that we're lucky to get to 120 knots with a stiff tailwind, but to actually get military planes, get commercial jets, get military planes, get very high-speed hypersonic vehicles, either for civilian or military use, and a single stage to orbit, potentially even vehicles, all electrified, would be of tremendous value from the point of view of green energy, from the point of view of climate preservation. So my suggested way forward is to partner with MHD researchers that have done work on this in academia in the past, get going on the device-related physics and fabrication, the wind tunnel testing. There are underutilized wind tunnels all over the United States, all over the world, that we should be kept busy. They should be being kept very busy with this. And it's really a crying shame that we have these incredible wind tunnels, including at NASA Ames here, that sit idle at least 90% of the time. Develop an IRAD program funding these technologies, and no bucks, no Buck Rogers. We'll need the funding, either private, public, or some combination thereof. It doesn't necessarily have to be all the mainframe, regular mainstay Boeings and Airbuses of the world. They could partner with device physics companies, with actuator companies, Collins, United Technologies, make a pretty good trade in the area of billions of dollars on these linear actuators. I would think they would be motivated to become part of this. So it's those second tier suppliers too that we could potentially leverage for this technology. And that would be part of the supplier base if they're willing to help develop these MHD devices on their own IRAD. There would be a lot of incentive in terms of potentially capturing that intellectual property. I wanted to do some acknowledgements before I wrap up. I did have a French aerodynamicist look at this, Cécile Cassie, and I wanted to acknowledge her careful review of this work. It added another couple of figures when she asked about some of this, and it greatly improved the talk. And also William Reichen for introducing me to some of the other aerodynes that are out there, including one by Dr. Mirabeau. These are some of the figures of Mirabeau's design, which includes this laser-induced air breakdown, this air ionization that's laser-induced, that's a precursor to the vehicle that shows you don't necessarily have to ionize just at the skin of the vehicle. You could do some pre-ionization, and there may be some benefit to that. I think that's it for my talk. We can go now off the slideshow in case there are any questions.
Wonderful. Gary, well, thank you. Before we do that, I want to put this on gallery. Everyone, please give Gary Stephenson a giant applause for a wonderful presentation on MHD. And Gary, thank you. That's something actually that I think we've neglected, right? I mean, it's aerodynamic, but it's still alternative propulsion. And what intrigued me was you'd kind of touched on control surfaces for the Tic Tac, and so that interested me.
Yeah,
So,
yeah, no, thank you for that. It is intriguing. Clearly, the Tic Tacs are doing G-force maneuvers that no human occupant could ever survive. But it is intriguing that it has such a similar shape. That capsule-shaped aerodyne.
Yeah, well, and it's one of the things that interests me, and before I go to questions, is so presumably they use some kind of field effect propulsion, right? But they still have to operate in a medium. They still have to operate in multiple mediums. And again, one of the things that I feel like a broken record saying this is, for me, that makes this extraterrestrial origin more plausible, because if you're designing a spacecraft, you're going to want it to be able to go into like Jupiter or Uranus or any of those kind of planets with varying thicknesses of atmospheres. So it's not just going to be moving through air, it'll be moving through stuff that's as thick as the ocean, right?
Multiple mediums. Right?
Multiple mediums, yeah. So having solid state control surfaces makes absolute sense if it's field effect propulsion, because you're still going to be moving through these mediums. So